So for the last year or so, I had run into something when I was trying to make a command line tool for doing automated mathematics, where you could have a command line. You basically do like push and pop on expressions, and wanted to do it because geometric algebra was so kind of unwieldy to manage without any tools, and almost nothing like handles non-commutative algebras correctly, because in geometric algebra, in the same way that when you do subtraction or division, you can't just like swap the arguments because it'll basically like mean the inverse of it. Um, right? If you say 2 minus 1 versus 1 minus 2, um, you get different results. Same with matrices. Um, but in doing this, I started running into problems, and it kind of leads to all these stupid arguments that people get into on the internet about mathematics. And the funny thing is, it's like you can actually have two like real mathematicians who totally disagree, and people that are good like in their area will absolutely say that, yeah, this thing you're doing, it like does not work, but they're both mathematicians, and it's like there's like there should be one mathematics, but there apparently isn't. There seems to be like a fundamental agreement on what the equal sign actually means between some people. So what I'm going to do is I'm going to go through something that's truly ridiculous, and you might argue with me that it's not right, but then I'll argue and tell me where the step that is wrong, because you can't object to the end result. Mathematics, it's a bunch of axioms. It's a proof is like a graph that leads from one place to another, and you start with axioms that are like circles and then there are like arrows between them, and so axioms are things that you believe to be true as like end results, and then you have rules, which are the arrows between the things that you're calculating. And so if axioms and rules lead you to something, I'm sorry, you have to believe it. If you don't believe it, you have to find a rule that has been applied wrongly, or you have to find an axiom, and you have to identify them. You can't just do a bunch of mathematics steps and then object to the end result. Because if you could do that, then someone could show you a proof of something, and you could stand up in the back of the room and just say, I just don't believe it. So, let me tell you what I'm talking about. If somebody says to you that it's true that -1 is, well, if you add infinitely, 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus dots, that is going to be equal to -1. And the reasoning is, it looks ridiculous. It looks ridiculous because if you add a bunch of numbers that are finite and positive, then you're always going to get a finite and positive number. And so you have this situation where just because you added an infinite number of them, you got something that breaks the rules. So this is like one sequence that some people object to, and the one that everybody argues about on the internet. You end up getting it in a very similar manner. Say -1/12 is equal to 1 plus 2 plus 3 plus 4 plus 5 plus dots. That's an actually more famous one. If you object to this one, -1/12 is the sum of all integers, on the grounds that it's ridiculous because how can you have a negative fraction? Then you probably, I can't see how you also how you might believe the first statement, but you can't accept the second statement. Other than like the proof of one of them, like having like a step that you don't believe, but having but picking a bad proof to show that it's wrong is not the same thing as showing a proof that is not wrong, because that's like a great thing that people do on the internet. They'll find a bad proof and they'll use the bad proof to try and tell you that something isn't true. Well, no, bad proof is an irrelevant proof. You need to find a good proof, and find what the problem is. And if you're using computers, it's like there's like no reason why you can't find the exact step that you object to and say we can't go any further. Okay, but the first one is really, really easy to prove. It's absolutely elementary algebra. All you need to do is rely on the notion that if you say that A is equal to B, then what that implies is that A can be substituted for B in one direction, and B can be rewritten to it as well any other direction, right? So if you accept that this is what the equals operator means, there's certain objections you can't raise, because if I do a bunch of algebraic manipulations and I do in fact come up with -1 = 1 plus 2 = 4 for those 60, then the burden is not on me to say like why the result came. You got to find the wrong step. If you can't find the wrong step, then you have to accept the result, or have somebody else more qualified find the wrong step. Okay, so let's do this. So we have a sequence that is 1 plus 2 s. And what we're saying is there's this thing that it can be recursively defined as 1 plus 2s. And if we can solve it for a value, then we have to accept that it is that value. So if we take s and we subtract 2s from it, minus 2s is equal to 1. And that's a consequence of the first statement. And we say 1 minus 2 times s is the same thing as that. Is equal to 1. Right, so we're just rewriting it basically. So if we have s minus 2s is equal to 1, and we filter that out, and then we end up saying that minus s is equal to 1. So whenever we see the value s, we can always substitute in a minus 1. Right? S equals minus 1. So if we go back to the original statement that started this, 1 plus 2s. Well, what is s? It's 1 plus 2s. And at this point, we have people that don't believe in recursion because, like, maybe they've never used a computer before or something. But this recursion is completely valid. We can actually start with a value. A statement of s equal to minus 1, and we can actually produce s equals 1 plus 2s from it. So you can't get out of this by objecting to the recursion. But if you keep substituting this in, 2 plus 4 plus 8 plus 16 plus 32, and this is really, really crucial, you cannot say plus dot dot dot. If you say plus dot dot dot, you can come up with any wild conclusion you want because it's not specific enough. You need to be able to actually compute the end result. So the pattern for this is you get 2 to the 0 plus 2 to the 1 plus 2 to the 3 plus 2 to the 4 plus dots plus 2 to the n. But this thing that's multiplied times s, it goes beyond that. So 2 to the n plus 1 times s. And this is like a really, really, really crucial point. It says plus dot dot dot, but it doesn't mean anything if you stop there. say, if we say that I'm telling you that if you say plus dot dot dot, it's nonsense, because it's not nonsense in that we don't know what you mean. It's nonsense in the sense that you haven't specified what the procedure is. And of course, the problem that you have is you can't write down an infinite number of anything. But that's exactly why it doesn't work. You can't iterate an infinite number of times on anything. So from there, let's go back to this equation where we say 1 plus 2 plus 4. What's actually happening is you have a sequence S, and you're saying that it has some value, and you're not specifying what it is, but if you're going to have a summation of some stuff, you say, we're going to have a whole bunch of stuff that adds from 0 to n, and then we're going to have a tail that gives us everything that we were not able to write down. We got tired, we wrote down what we could in the sum explicitly, but for the tail we gave a formula that says how it goes for the rest of it. We can't actually write out the whole tail because that would involve like writing an infinite amount of stuff. It would involve an infinite amount of work. So that's the reason why the tail actually exists. If you'll notice, if this is going to be like 1 plus 2 plus 4 plus 8 plus dots, and then you have to include like what the tail actually is. So if you get up to 2 to the n, and then you have 2 to the n plus 1 times s, what this means is that it's going to look like the original sequence we did before. We just substitute it in. So 1 plus 2 plus 4 plus 8 plus dots. Right? That's like what it means. So I can say 1 plus 2 plus 4 plus 8 plus let's find like we'll just use a finite value. Say that we got up to 32, and then what comes after that is 16. Right, so we have 1 plus 2 plus 4 plus 8 plus, I'm sorry, 64, plus 1 plus 2 plus 4 plus 8, and I'll just fill in, I won't bother with the dots, plus 16, because that's as far as we went, plus 32, plus 64 times 1 times 2, so it means you have 1 plus 2 plus 4 plus 8 plus 16 plus 34, 64 plus 128, 256, whatever. So what we're saying is we have we're saying that the recursion is a valid representation of this because it leads out to this infinite pattern, and because it has that infinite pattern, anything you conclude from it must be right. But what ends up happening is we've already solved this for the value of -1. So if we were to figure out like what's the finite value of this, because if we say that s minus tail Sn is equal to the sum for some finite number of these values, then what we're saying is we should be able to solve for it, and it actually does, and that's the really amazing thing. That's the part where you really got to believe that there's something to this. N plus 1 times s is equal to some in this case, we'll just write down 1 plus or 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus dots, Remember, that's not an infinite number of dots because I claims our algebras become suspect if we use an infinite number of them. Alright, so if you add up the powers of 2 from 0 to n, then you end up with this. And remember that we say s times 1 minus 2 to the n plus 1 is equal to that. And then what we do is we actually put in minus 1. 1 minus 2 to the n plus 1. So what that means is we swap them around because s is equal to minus 1. So what that means is we swap it to be this minus 1. And this is like really profound because what it says is if you represent your quote-unquote infinite sequence, the reason why you get this paradoxical result where it says minus 1 on the side is that you've collected, you know, this infinite value on the tail is on this side, and the tail is going to give you something that's not finite because this is large, but then also the tail is negative large because we have to cancel it to give it the constant value that it has. And what this is saying is like if I expand the sequence 0 times. And this is what n is. It's the number of times you expand the sequence. If I expand it 1 time, 2 times, 3 times, it always has the same value s because we're talking about, you know, the infinite sum. So what we're saying is as n gets larger and larger and larger, this is the value that n has. And the limit of this, whereas n goes to infinity, is it's an infinite value. It's an infinite value. Doesn't really have a value because what you do is you say 1 trillion and it says no, it's quintillion and it keeps getting larger and larger. So it doesn't really have a value. That's what you say when you say that it's infinite. What you're basically saying the direction that it goes to. And through iteration, you're never going to reach the end result, right? So if you never reach the end result, then why are you objecting to it solving for minus 1? Because what I've just shown is you can start off with a statement that s equals minus 1, and you can manipulate it to make a recursive equation, and recursion is valid because you're just substituting equals for equals. And if you keep substituting s into it, this is the proper way to write an infinite series. If you can do it, I can't always find a way to do it. But if you say 1 plus 2 plus 4 plus 8 plus 16. And you say, well, 32 times the sequence. And so if you have any dots, they need to be finite. So that if you're asked to actually write it out completely, you can write it out completely. But you can only name an n that you can go out to because you can't literally write an infinite number of them. And then when you get to the point where you've written the highest n that you can do, you say, well, I just got to say 2 n plus 1 times s. But the s on this side is a large positive, and because this is a positive finite number, then this has to be large and negative, right? And what you do is you subtract this from this, so sum minus tail. So what you're saying is when you say that if you say 1 plus 2 plus 4 plus 8 plus 16 equal to negative 1, the only reason that's wrong is because the sum is equal to s minus tail. It is not equal to s. The only time it could be equal to s is if you had a sequence that got smaller and smaller. So if we say z is equal to 1 plus, say, fraction of 1/2, then what you have is you have 1 plus a half plus a fourth, and in fact we'll make this even easier by making, just call it 1 half plus 1 half s, or 1 half z. So what you're saying is if you add a half plus a fourth plus an eighth plus a 16th, then it's going to be equal to 1 in the end, right? Because you can solve this for the value 1. So instead of using a half, if you use 2, you end up getting this sequence where it ends up solving for -1, and people object to that. But the thing is, if you were to quote unquote add an infinite number, you can't actually do an infinite number of iterations. So there's actually no paradox. There isn't a paradox because what you're doing is if you want the actual sum, you want a limit that goes to infinity, then you say s minus tail. But if you have a situation where the tail goes to 0, as n gets larger, then that's what people are thinking when they say, for this sequence z, for instance, it's a 1 half plus 1 fourth plus 1 eighth plus dots plus 1 over, and in here 2 to the n plus 1 over 2 to the n plus 1 times z so 1 half plus 1 fourth plus 1 eighth, and then you keep going until what you're saying is this sum here, this literally is the sum from 0 to n, and because z is on the other side, then you literally have to subtract to do z minus 1 half to the 2 to the n plus 1 times z. And this is super important. You can't just put dots in this. What you're saying is that whole sum from powers from 0 to n, this is the formula to reproduce it. But the thing is, because z, we can solve z for 1, right? So we say 2z is equal to 1 plus z, and then you, let's actually explicitly solve for this. So if we say 2z is equal to 1 plus z, and then we subtract z from it, and we're saying is z is equal to 1. And because z is equal to 1, anywhere you see a z, you can drop a z. So you can say that 1 is equal to 1 half plus 1 half, right? And so what we're saying is we have 1 minus 1 half to the n times 1, then that's actually just the same as just writing it this way. 1 minus 1 half, or 1 to the n plus 1. So that's a closed form for all this stuff that we added up, right? So it's kind of like doing integration. We come up with the formula for everything from 0 to n. But what we come back to is nobody argues with this result where if you add a half plus a fourth plus an eighth plus a 16, and if you quote unquote go on forever, the value ends up being 1. They do object to this like more like a P-adic notion, where if you had 1 plus 2 plus 4 plus 8 plus 16, you end up in base 2 with a string of 1 that go on infinitely. So it's like on a computer register where you turn all the bits on, and if you were to add 1 to it, the value comes out to 0. So what it's basically saying is it wraps around. And this is only done by using substituting equals for equals. I'm not doing some weird mathematical system where I made some different assumptions. This is like normal mathematics. And the thing is, you need to be able to start with the axioms and you apply the rules. And if you reach a result where it says, sum of a bunch of powers of 2 ends up being -1, what you're saying is this object has the property that if you multiply it times -1, you get 1, or if you add 1 to it, you get 0, which means it's basically the largest number. So another thing about infinity, dealing with the largest number, they're not comparable. Once they're infinite, you can't say that like one is greater than the other. For instance, if I say dots, and I say 82, 82, 82, 82, and how does that actually compare to a whole bunch of dots to the right, or to the left? I mean, 90. Let's see, 19, 19, 19, 19. So, because this number has never-ending digits going to the left, and this other number also has never-ending digits going to the left, people call this infinity, quote unquote, but they're not the same value. In fact, if I find a recursive equation for this, I can solve it for it, and it will be a finite value. And because this is a large positive, it's probably going to be like a negative number, and it's probably going to be a negative fraction for both of these. For the same reason that when we come up with dots 9999 in base 10. In fact, let's actually show how I should write these. So let's say that this is in base 10. This is in base 10. And this is the number for which if you were to add 1 to it, it becomes 0, so that's also in base 10. But then there's also this other one which is related to things that people argue about on the internet. If you have a string of 1s, and that is in base 13, then that number is equal to -1/12 as represented in base 10. And it's literally the finite -1/12. It's just that it's like another representation of the number. So what this means is there are some numbers, I believe for all finite numbers, there's going to be like equivalent strings of digits that have an infinite number of digits that actually are the same number. And it's not any weirder than 0.99999 is equal to 1. It's because in that case, it's like an uncarried representation where because there's no zero somewhere in the end, it has to ripple carry. You don't need to add anything to it to make it ripple carry. In any case, these are all quote unquote infinite numbers in the sense of they have an infinite number of digits, but they're actually finite numbers when you actually analyze them. Because if you look at some patterns are going to be negative integers, and other patterns are going to be like negative fractions, negative rational numbers. In any case, that's my video. I'm just testing out using LaTeX live coding for something that I've ran into, and I now fully believe the -1/12 proof, although I don't like one of the steps that is usually used, and I actually found a way to actually do it where it's actually quite believable, like machine computable, finite, and you actually don't have to believe in infinite processes to believe the -1/12 is equal to sum of all digits, in a sense that if you were to write down the recursive equation for it, then yes, it comes out to this number here, 1111111 in base 13. Right, and I can show why that actually happens like right now, trivially. So if I have say y is equal to 1 plus 13y, you can go ahead and solve that. It solves for -1/12. And if you keep substituting in y into this equation over and over and over again, it's the sum of all powers of 13. So it's 13 to the 0 plus 13 to the 1 plus 13 to the 2, on and on and on, is equal to negative 112. And I'm not in a weird number system. I'm like in the normal number system. But this happens because of substituting equals for equals. So that's the end of the video. I need to figure out how to turn it.